And if you want to do details, you can work out the similarity and actually get algebraically that a squared plus b squared equals c squared. But the proof I think is in the picture. Okay, so that's the first proof, proof 1. It has intrinsic fit. Why is that? Because the idea of it is exactly what the Pythagorean theorem is about. So the proof fits the theorem. It sort of just tells you what it's about. And I'm going to contrast that with one that doesn't. So this proof is, I don't know if you've seen this. This is proof using trigonometry. Because long thought you couldn't use trigonometry to prove the Pythagorean theorem, but Jason Zimba has done it. He uses the law of sines and law of cosines, and he's able to prove those non-circularly, so he doesn't have to use cosine squared with sine squared equals 1. And yeah, you just get it out. You say, look for cosine of y, add and subtract x, apply cosine, law of cosines, multiply everything out, and you gather your terms, and then you get cosine of y equals cosine of y times 1. So this times this thing, which we want to know. And that means that thing has to be 1. And the cosine squared plus sine squared equals 1 is equivalent to the Pythagorean theorem. Okay, so this is an example which I think is not very explanatory, an example that doesn't have intrinsic fit because the proof doesn't have anything to do really with what the Pythagorean theorem is about. It proves it, but it goes outside the domain. It uses trigonometry, and you don't really get an insight into why it's true. It's cool, I think. It's very beautiful.
But
so,
very circular because you need the Pythagorean theorem in order to.
It's not circular. You don't need the Pythagorean theorem to derive the law of sines and cosines. That's what he established in his paper.
Right, but that might turn out to be the core of the. I mean, it could be that bit's explanatory, and that's the bit that you haven't shown us. It could be that if you fill that proof out, yeah, you've used the law as a lemma, but it could be that his proof of that lemma.
It's clean. Yeah, it's clean actually. But anyway, let's go on. So in my seminar we voted on these proofs, which did people like better, which one's more beautiful, and all the mathematicians agreed the first proof was beautiful. ME means math educator, M means mathematician. And in this particular case, the math educators who liked proof 2 better said that they didn't really understand proof 1. And that's actually part of a problem with this empirical data because your level of understanding obviously affects your judgment of how beautiful something is. So that's kind of noise that we have in our data. Okay, I don't know if I have time for this, but I've tried to list out some features of intrinsic fit. So what is it that makes a particular proof fit a particular theorem? And I'm very happy for feedback on these. These are sort of new things for me to write about. And they overlap a little bit with Paul's list, so it's kind of cool. Anyway, one of them is economy. So how concise something is. I didn't include elegance with economy, but anyway. Transparency, how well can you see the underlying idea? When you read the proof, do you see immediately what the underlying idea is, or do you have to do some work to get back to that? So in the trigonometric case, it's not transparent at all. Maybe there is an underlying idea that tells you exactly what the Pythagorean theorem, why it's true, but you probably have to do quite a bit of work to do that. But with the Pythagorean, the other proof, you see it right away. Meaning, so you get a sense of meaning from reading the proof. You can see what's going on. And symmetry is there reluctantly, but it's there right now. But the proof exploits some sort of symmetry that's internal to the given argument. I'm not sure if there's any symmetry in the Pythagorean theorem proof, the first one, in this case. Similarity, yeah. It's not in all of them. I'm not sure. In a lot of our examples, we have some symmetry. I don't think there was in that example, but not all of these criteria have to be met for a proof to have intrinsic fit. These are just some of the ones that seem to come up a lot in our examples. Okay. Now I'm going to show you examples of extrinsic fit. And I'm going to use Pick's theorem. Have you seen that before? So 2 different proofs of Pick's theorem.
There are 15.
Yeah, okay. I'm going to just show you 2. One of them is from proofs from the book. That's kind of a famous one from proofs from the book, and another one is the one a mathematician friend showed me. So the theorem is, this is done often with 5th graders or so, just to verify that if you take an area of a lattice polygon, that's a polygon that has vertices on the lattice, that you can calculate the area by this amazing formula. The number of interior points, I, plus half of the boundary points, minus 1. So pretty cool that that formula works, no matter what lattice polygon you have, whether it's convex or concave. So in this particular case, the area, there were 11 interior points, and there are 10 boundary points. So the area is 11 plus 5. Oh, it should be minus 1, right? Yeah, that's typo. Minus 1, so it should be good. Okay, why is this true? I'm going to show you 2, just really quickly, 2 proofs. These are both proofs by double counting. The first one, you add up, it deals with the interior angles. So I triangulate the polygon. You have to prove that you can triangulate, but we're going to assume that you can triangulate. We're going to assume that the area of all the interior triangles is 1, which is not trivial to prove, but I'm going to assume that. So these are, sorry, 1/2. Okay, so I triangulate the polygon, and there's 2 ways. And we say that there's n triangles inside. There's 2 ways to count up the interior angles. One is we have n triangles. Each one has angles that sum up to pi, so n pi. The other one is to think about the points. So around every interior point, I get 2 pi. And then around every exterior point, well, it's hard to count each one individually, but if I think about taking a trip around the outside, then I'm going to get, I'm going to overcount first. So just say that I get pi for every exterior point, which works fine if it's on the edge. And if it's on the vertex, by the time I've gone around the whole way, I know exactly how much I've overcounted by, because I've gone around the circle. So I need to subtract off 2 pi. So that's that term there. So I've counted up the number of angles in 2 different ways. 1 and 2, I set them equal, cancel out the pi's. I get n equals 2i plus b minus 2. And n is the number of triangles, and the area of each triangle is 1/2. So if I multiply by 1/2, I get the formula. That's proof number 1. Proof number 2, I'm afraid I don't have time to go through in detail, but it's kind of cool. This is the one in proofs from the book. It's an application of Euler's formula. I don't know if you've thought about that, but this lattice, it can be thought about as a graph. So if you take, it can be thought of as a polyhedra that's flat, where the outside of it is considered to be one face. So if you do this double counting in an appropriate way and use Euler's formula, you can get the formula also that way. Yeah.
Could I ask what your definition of cool is?
I don't have a definition.
Commonly used adjective one discovers.
I have a colleague though, when I have a grant to study beauty of mathematics, and I have a colleague who does graph theory, and he told me, yeah, it's okay that you got the money, but it shouldn't be about the beauty of mathematics, it should be the coolness of mathematics. It's really all the examples that I'm talking about are cool.
They never
not
would be
beauty.
the grant if you said it that way.
Yeah.
So they're not synonyms.
Anyway, so I wanted to say, okay, so both of these proofs, I think, exhibit, I'm not talking, they may have some intrinsic fit also, but what I want to highlight is their extrinsic fit. They're fit into a class of different kinds of proofs. So the proof 2 is pretty obvious. That one is an example of an Euler theorem proof. And what's cool about it, or beautiful, or neat, or whatever, about the second proof, is that, oh my gosh, I can use the Euler's theorem even here. I didn't know this was an Euler's theorem proof. It wasn't obvious to me when I looked at this lattice polygon that it had anything to do with Euler's formula, but it does. So that's why proof 2 is nice. And proof 1, it uses a technique. It uses a specific technique of looking at angle measures, which isn't obvious either. And that's a technique that can be used in many, many different settings, and it can be used here. This tool can be used even here. And these are what we're calling two different representations of different kinds of fit. The first one, the angle measures, is an example of connecting a general technique, like using angle measures, to a particular case. And what gives you the feeling of beauty about it is, this little tool works even here, breaks open the problem for me. And the second one is, we're calling it generality, going from a specific to a general. So we have this class of things, all of the things that can be proven using Euler's formula. And you realize, this is a family membership. This one also belongs up there. And that's a kind of fit. That's another way of thinking of that, another kind of extrinsic fit in contrast with the first one. Okay. So I try to also list some aspects of extrinsic fit, like we did with intrinsic fit. And I'm not really not sure about these, but it might be related to generality. So the idea that a proof generalizes to a larger class of theorems. And it might be related to unification that we talked about earlier in terms of explanation. So some theories of explanation have to do with unification. And it might be what gives you, the sense of fit is that you see that this set of proof collapses into one. You have one basic underlying idea, and that works for a whole class. And that's what gives you the family membership. Okay, this is my last slide, actually. Okay, so if I was more technologically adept, these things would, not show up now. But anyway, my PowerPoint did very strange things this morning. So these are the list of the things, some of the things that characterizations that we have for fit at the moment. I'm not sure if they're all right. And whether or not they apply to beauty, whether or not they apply to explanation. And this is what's sort of giving me the idea that these are related. I may be wrong about this. I'm not sure generality really has to do... Why did I say no for beauty? I know why I say no for explanation, because I think Mark Steiner has a pretty convincing case that he gives examples of general proofs that are more general but aren't more explanatory. I was convinced by those. But certainly those of you who thought that the picture proof of the arithmetic sums, well, if you think that the standard proof, where you add up the two sums, is not as beautiful as the picture proof, then you would put no for generality there because the picture proof wasn't general. But I think that one was highly debated among you guys, so I don't know if I should put that stuff out on that. So anyway, I think I should leave this as an open question. If you buy, there's several things that I'm putting out there for critique. One is whether this is a reasonable characterization of fit. And the second is whether or not there are these connections both to beauty and explanation. If there are, then I think I can make a case that the two are related. And I actually don't mind if some of these things are mismatching. I don't think that there's a perfect, I don't think beauty is the same as explanation. Those seem like different concepts. So they don't have to match on every variable, but I guess I'm looking for match on a significant number of variables that one feels like they're related. So we'll get back to this in a second, but I just want to thank the other people I work with. Manya Raman is my collaborator. He's a mathematician at New University. We have a big group of people who helped us a lot. I did a lot of this work and presented it at ANU in Canberra this summer, or their winter. They gave me good feedback and the money I got from the university for doing the work. Thanks.